stuff organized here. Still got time. Okay, so I think I'm organized. Let's just shut the door. So I just want to go over this aspect that we were thinking about yesterday, and how it comes sort of like why we make this division of the distance of determined by peak A to the rest of them. So I just want to go over that so that we are kind of clear. The object, what we're trying to do is assign indices to these peaks, remember? So what we know, where should I put this? I'm still not sure which screen is which, but let's have a go. Yep. So this is what we got there, right? So it looks it doesn't look very good. Anyway, I think you can see it's over here anyway, okay? So let's think about what we know. We measure these things, so we know these, okay? Those are our results. And we know that the distance between lattice planes is equal to A, the lattice constant, over h squared plus k squared plus l squared. We know that, and we know this relationship. It's equal to lambda over 2 sine theta. So those are the things that we know for sure. So when we look at the sine function, it looks like this, okay, where this is theta. So what we can see is that for the smallest angle, namely A here, so let's write for the smallest theta, that will give rise to the smallest h squared plus k squared plus l squared, just from this relationship here. Now, if theta is small, we get a small value of sine theta and a big value of the interplanar spacing. So for the first smallest peak, we will get the set of smallest Miller indices, and we will get the largest interplanar spacing. So this first point is probably quite important, that for peak A, smallest angle will give us the smallest HKL values. Okay. And we also know another thing about the HKL and also the h squared plus k squared plus l squared. We know it has to be integer. Okay. So we also know h squared plus k squared plus l squared has to be an integer. And I think that's probably about all we know at this point here. So if we focus on peak A, it will have the smallest h squared plus k squared plus l squared. So what we did before, remember up here we made the ratio of dA squared, that is the distance corresponding to peak A here, to that of the ones below. So if we just look at that, dA squared, let's do it with respect to dB squared. So we are just looking at the first ratio where we get 1.3. Just write down the expression for your term. That will be equal to HA squared, where A represents peak A. Okay? So HA squared plus KA squared plus LA squared. Then we're dividing it by the corresponding quantity for peak B. So that turn it upside down, that turns into multiplication HB squared plus KB squared plus LB squared over A. Okay, so we can see that the A's cancel out, and we only need to, we're only concerned with the relationship between the indices for peak A and peak B, which are related by, sorry, one more thing. And we know, of course, that this is equal to, from our expression here, we know that that's equal to 1.333. So then we can say we need to find HB squared plus KB squared plus LB squared being equal to 1.33 times the Miller indices squared and summed for peak A. And I think that's basically, all we have got. We know that these have to be the smallest Miller indices, the smallest quantity. Okay, so we start off with this, and we know it has to be an integer. So, for example, if you would put h equals to 200, this would get you 4 times that. What's 4 times 1? It's not going to work. So that's basically how it has been determined that for peak A, these have to be a 1, 1, 1, because this is the smallest indices that will get you an integer, okay? Because this has to be an integer, and when we multiply that, we also have to get an integer because this is an integer. So that's times 3, and that's kind of how we got this. That's kind of how we deduced that this was 3, just by knowing it has to be an integer, it has to be small. And that's how then we get the 4 up here. Okay, and you can do the same thing. So there's a little bit more thinking to it than just saying, oh yeah, we find this number 3, which we do just by looking at it, but there's a little bit more thinking behind it, I suppose. So if you do the same thing for peak B, we will get here we're considering peak A over peak B. Here's peak A over peak C. So the same thing over peak C. We get, in this case, 2.69 from here. And we can also put that equal to our HKL. In this case, it's going to be HC squared plus KC squared plus LC squared equals to what am I doing? Sorry, we've got the same thing here, equals to 2.69 times HA squared plus KA squared plus LA squared. Okay, so in this case we've already found that that should be 3. And so in that case for peak C, it has to be equal to 3 times that, which was about the 8 there. Okay, is that clear? I hope that's clear. I actually learned something, so yeah, that was good that you asked the question. Yeah. Yeah, okay.
Sorry. Why can't you just take 0, 0, 1 for the Miller indices? Why is the trio 1?
Oh, you always ask the very good questions. 1, 0, 0. Yes, that would indeed give you the smallest set of HK. The trouble is, when we multiply it by that, it's telling us that it's not an integer. Yeah, I think this B's will have to be an integer too.
Okay.
So that's, yeah, yeah. Okay. we kind of finished all we're going to be doing on crystals and diffraction right now. So what I've got on this end of this lecture is just some little summary questions to help you remember what you might have forgotten through the lecture. These are not necessarily, these won't be questions that you get asked on the exam. They are just statements and questions to help you remember sort of what we've been doing. Like define a Bravais lattice. What is a Bravais lattice? What is a primitive vector? What is a Wigner-Seitz cell? Construct the Brillouin zone for a two-dimensional square lattice, a hexagonal lattice. What is Bragg plane? What is X-ray diffraction? What are the 5 types of bonding? And how large is the typical lattice spacing? Just some questions to help. Also put some kind of little brief summaries about things related to what we've been doing. I guess I don't need to go through them here because they're kind of summary things. There's your reciprocal lattice vectors, which are really kind of important for you to remember. There's the Bragg scattering, 2d sine theta. And there is the important structure factor that you have just seen. Okay, so this is kind of a new little topic on electrons in periodic potential. So we now have looked at our crystal. We've looked at how to define certain planes. We looked at scattering. But what we want to do now, and we've looked at the free electron model, okay, where we have had no potential, only a periodic repeating box. So now we are basically going to put in a potential, and the whole aim of this is to look at Bloch's theorem and kind of do a little bit of a derivation to show you how Bloch's theorem arises, which Bloch's theorem will get a wave function for an electron in a periodic structure. And we'll see what form that wave function has. Okay, so what have I written down there? Let me see. Okay. Yes, we're going to set up a formalism basically to derive Bloch's. This is really nicely explained in more detail in Ashcroft and Merman and also in the Oxford Basics text. So it does a much better job than what I can try and present here. So, as you know, when you've got electrons in a real solid, it's a many-body problem. You've got all of the electrons of all of the atoms interacting with the ion cores and interacting with all the other electrons. It's not solvable. Even today, it's not solvable. I guess quantum chemists think they are quite close if you look at very small molecules. And there are very accurate ways that we can calculate it, but it's an approximation still. So just to say that. So it's impossible to solve exactly. So what is the model? As I said before, we've seen the free electron model. So now we're going to build in a potential, and we're going to consider the independent electron approximation. So it means that the electrons don't directly interact with each other, but they can interact with an effective potential that the other electrons give rise to. And so this is called an effective potential. So if you're an electron, and you've got a lot of other electrons around you, you don't sort of interact just with every other electron on a one-to-one basis. But if I'm an electron, I can maybe feel the potential energy of all of you as a whole, right? And so you are like an effective potential, if you like. But I don't interact one-on-one right now. And it's also periodic. Okay, we know because we've got a solid, we are always dealing with crystals and assuming that they are periodic. This shows the position of an atom or an ion here, and this is what a potential looks like. And we call it V of R. Sometimes it's called big U of R, so just be aware. Okay, remember we had, for the completely free electron, the equation here for the Hamiltonian, momentum squared divided by 2m, and the energy h bar squared k squared on 2m. And remember the resulting curve that it looked like, the free electron curve? This is the curve for free electron. This would be at a gamma point. Okay, now because we've got periodicity and we've got reciprocal lattice vectors that take us from one unit cell into another unit cell, in reciprocal space we're going to have all over the place, at every reciprocal lattice vector we're also going to have this same kind of relationship here, because we have the periodicity of the reciprocal lattice as well as the real lattice. So you can imagine, it's a little bit hard to imagine, but here, here we are in reciprocal space or K space. This here is, if you define this to be the origin of your reciprocal space, then this is what we call the gamma point, 0, 0, 0, and it corresponds to this curve here, if you like. Now, if you go over to the right, you will hit, this is another reciprocal lattice vector, okay, G, and on this point here, there will also be this energy curve here, okay. You go the other way here, this other reciprocal lattice vector, there will be another curve here, and so on and so on. This is sort of drawn in the so-called extended zone scheme. What we're going to do later is basically fold everything back, so we only need to worry about the first Brillouin zone, as I mentioned earlier. Okay, so we start off with considering a weak periodic potential, and it's called V of R as given here. Okay, and again it's periodic, and the big R is your reciprocal. No, in this case R is not a G, sorry, it's a real space lattice, because this is in real space. Okay, and these are your real space vectors. Okay, let me just say, we've used Fourier transforms before because our system is periodic, and we're going to do the same thing here. So we can express the potential V of R as a summation over reciprocal lattice vectors, some prefactor here, V of G, and e to the I reciprocal lattice vector dot R. Okay, and you know the inverse Fourier transform is just given by here, where in this case V of C, there's quite a lot of V's going on here. Okay, this is the potential in real space, V of R. This is the coefficient when you expand in a Fourier series, V of G, and V of C is the volume of the unit cell with which we are normalized to. Okay, that's nothing new. Okay, so what do we have here? Here's our Schrodinger equation. Okay, here with the periodic potential, you've got your wave function, you've got the energy eigenvalues, and the important thing is what we're going to do is try and find an expression for that wave function psi. Okay. And as I mentioned before, it's a one electron wave function, and we're assuming the independent electron approximation, as I mentioned. And in a periodic system, these are known as, these will become block waves, your psi, and in a periodic system, our electrons are called block electrons, after the famous person that developed this formalism. Okay, clearly, as I put here, when the potential goes to 0, we just have, you know, your situation for free electrons. So all we've done is introduced a weak potential in this case. So we're going to expand the potential as a Fourier transform. We're also going to expand the wave function as shown here over plane waves. So we have a sum over all k vectors in reciprocal space here, or for some set of k. this is the coefficients that we will need to determine, and here's plane wave. So you might be able to guess what we're going to do. We're going to substitute these expressions into the Schrödinger equation. Let me see here. Got that written down. Where's my stick? I think it's kind of straightforward. So what we've done, we've got these two expressions, expanding as a Fourier transform the potential, expanding as a Fourier transform the wave function, substituting them into expression 1. Okay, so in for psi here, we get the wave function. Here we have the potential and the wave function, because we are just expanding this now into that bracket. And the same thing here. Okay, then we just put these together in the same summation. Just put them all under a single summation over G, reciprocal lattice vector, and K, and adding those exponentials together to get e to the I G plus K dot R. And we can rewrite that as the below. Basically, we are just recognizing that this is periodic. E to the I reciprocal lattice vector plus K. Because it's periodic, we can just call it e to the I K dot R. Okay, so it's all good. So what we're going to do is just manipulate this equation a little bit. Basically, have taken the energy across from the right-hand side to the left-hand side and just put that energy in here. Okay, that's very straightforward. And when you do that, we can see that this inner brackets here can be equated to 0. Okay. Now this K vector is any vector in K space or reciprocal space. We like putting things into the first Brillouin zone, so we can rewrite K, any K that points to anywhere in reciprocal space, as being equal to a K vector, or Q, we call it Q in this case, minus a reciprocal lattice vector. So like when I drew that diagram and that cubic lattice, you can have your K going anywhere in K space, but it can always be written as, because every reciprocal cell is identical, we can always write that as being equal to a vector in the first unit cell, or the first Brillouin zone, plus a periodic, or bring it back into this reciprocal lattice vector. Too many words. Okay, so what we've done is just substituted that in for K, and made the substitution over here as well. What we are trying to get is just, we're trying to, overall thing, we're deriving Bloch's theorem. We are obtaining an expression for the wave function, but along the way, we need to know how to calculate the coefficient C. And you can see that this equation here basically specifies the coefficient C. Okay? So this specifies the C, the coefficients that are used to express the wave function. Because if we're going to express the wave function as this summation, we need to know what coefficients to use. Now, of course, you're not actually going to be doing any numerical practical classes, but in principle you could calculate these kind of things, which could be fun, but I think nobody's done that for you. It's not in your prac class or anything. Fine. Okay, so that's the equation from which you can derive the coefficients for the expansion of the wave function. Okay. Now, remember we had written the wave function as an expansion, the coefficients. Okay, we have this. So what we can do is just recognize that we can pull out it's only sum of the reciprocal lattice vectors, so we can pull out this e to the I q dot r out in front of here, which has been done here, and everything else is left the same as here, just pulling that, basically a plane wave, out in front of your summation, and calling this function here, or this expansion if you like, we're calling it little u. And this function here has the periodicity of the lattice, because it involves here just reciprocal lattice vectors. So this is basically Bloch's theorem. Just to say again, what it does is allows you to write the wave function of your electron in a periodic crystal psi as a product of a plane wave, okay, e to the I q dot r, multiplied by a function that has the periodicity of the lattice. That's it. What I could have is another equation, which I wanted to do, but I kind of ran out of time, just telling you that u, here this periodic function is just equal to this quantity here. Okay, but I think you can see that from the equation. So that's Bloch's theorem. So it kind of helps to have a look at what it's got there. So your wave function psi, this is just a one-dimensional case here, may look like this for your electron, and it can be obtained as a product of some plane wave here in the blue dash, multiplied by this periodic function u. Okay? And you can probably recognize that there may not be a unique plane wave and periodic function to get the same wave function. And that's indeed the case, which you can see not in the next slide, but in the slide after. This just gives you another example. I think it's always useful to see what these things look like. So this is your wave function, okay, that is obtained by multiplying a plane wave of some form with a periodic function. And the final one to show you there. Yeah, this is just a couple more examples. What is it showing you? Let me have a look. Okay, you can see that these two, these are wave functions of electrons in solids. You've got a real and imaginary part, which is shown in this case as blue and red. You can see that these are identical, okay? However, you can see that what they are made up of is different. So this result was obtained by multiplying the plane wave of this form with this periodic function. You get this. And this has two different kinds of functions, but when you multiply them up, you still get that. Okay, so they're not necessarily unique. Okay, so that's the important thing. The wave function of your electron in a crystal can be written as a plane wave multiplied by a periodic function. That's the main point. So what follows from this kind of thing? Anything that I haven't said already? The wave vector k, when you have this periodic system, it can be thought of like your wave vector for your free electron. However, it's not exactly the same, and it's not exactly electron momentum. It's called crystal momentum or quasi-momentum of the electron. Okay? So when you have electrons in solids, the k is not directly the electronic momentum. Okay? It's called the crystal momentum. Okay, what else? I think I've said this 1,000 times. The wave vector, any wave vector k, we can always bring that back into the first Brillouin zone just by adding or subtracting any multiple of reciprocal lattice vectors in the first, to bring everything back into the first zone, because that's where things are just unique. Okay. So what about u? We have an expression to evaluate c, the coefficients. We have an expression for psi, but we haven't as yet worked out how to calculate the functions u. And basically, they are determined by this eigenvalue equation here. Okay. What I'm just going to do is go through so you can see how we get that, because it's all very good to write it up there, but let's just have a look how that comes about. Yeah. How does that look? So remember, we had, that's not big enough. Okay. So we had the Schrödinger equation, remember? Hamiltonian electron wave function in your solid equal to minus h bar over 2m grad squared plus some potential. Okay, we had that, and let's call that number 1. And we had the block form of your wave function, psi of k of r, position vector r. I don't think I'll bother putting that on all the time. E to the I k dot r u of k of r. Remember? This was the important thing for today, the block form of the electron wave function. Let's call that 2. So basically what we're doing, we're just substituting 2 into 1, which you may have guessed already. So we end up with the Hamiltonian. We can give it a little subscript k, e to the I k dot r u of r over here, and minus h bar squared on 2m grad squared plus u of r e to the I k dot r u of r equals energy eigenvalue e to the I k dot r u of r. So that's kind of clear, but we just need to focus on this thing. So let us look at this thing. It has to operate on these two functions, so let's just call them f of x and g of x, where f of x is e to the I k dot r, and this is just u of r. And so, no, that's an f of x, g of x. Basically, we're just going to do this thing here. So first of all, we just expand in here. Do it on that one, keep that one, right? Keep this one, do it on that one. And do it again. Tell me if I make a mistake, if anyone's watching. Grad of g of x plus f of x grad squared u of, g of x. Okay, so when you substitute that in, you get I k squared e to the I k dot r u of r plus I k e to the I k dot r mu of r plus I k e to the I k dot r grad yep u of r plus e to the I k dot x grad squared u of r. And so you can pull this thing out one side and this thing out the other side if you want either I k dot r I k squared plus 2 I k grad plus grad squared. Okay, it's straightforward, but I do it any case for you. So let me see. Yeah, you can just either I k dot r I k plus grad. That's how you get the squared part there. So let's put it all back into equation 3. So we end up with h of k e to the I k dot r u of r equals minus h bar squared on 2m e to the I k dot r I k plus grad all squared u of r v of r e to the I k dot r and so on. And then, yes, we can actually get rid of these things. And I think that's basically what we wanted. Okay. Okay. Now, I'll just put this back up. I think that will be on the overhead if you want to go through it. So that's the way we got that expression up there. And remember we were dealing with a fixed volume. So the eigenvalues that we actually get will be, like in the case of a free electron, discretely spaced solutions of energy eigenvalues, and we call those n. So there will be, it's analogous to the case of the free electron in the box. Okay, so we'll get a whole set of energy eigenvalues. Okay, so what we do is the wave functions that we actually get out, they will be indicated by n, the actual eigenvalue, and k, whatever k vector we are dealing with. And that specifies the particular electron, the state of the electron. That's what we use to label the wave function. So, okay, just a couple more slides here. What's the point? The point is now we have an expression for the wave function. We know how to calculate the coefficient c. We know how to obtain the functions u. So we basically have derived everything we need to know. And you know how we had it for the free electron, like system, or the free electron system, it was just like this. And, okay, when we introduce a potential in there, what we find later on is we'll get little band gaps opening up. But basically, what we've got here, these dispersion curves are called the band structure of the solid. Okay? We could have called our free electron curves the band structure of the solid, but in that case, our solid had no potential. It was just like a repeating box. Another important quantity here is, say, once we calculate the energy eigenvalues, the energy here, okay, is a function of k. This is the energy as a function of k. You can calculate what we call the group velocity, and that's defined as the derivative of the energy dispersion curve with respect to k. Okay? So, for example, and we'll do it a bit later on, if we actually get a band gap here, which a lot of solids have, the curve will come up here and it will curve over here. Then at this point you will have the group velocity will go to 0 because it's just the first derivative. We'll get to that a bit later on, but perhaps put a red box around the group velocity. That's an important quantity. Okay, so in this picture here, you know, if this is the gamma point, our origin and reciprocal space, the curves in reality just keep going up. What's happened here is we have folded them back into the first Brillouin zone using a G vector. So this is important. This slide's important. In particular, the definition of the reduced zone scheme and the extended zone scheme. Okay, so here, this is just the free electron-like curve, okay, going up. Here, this distance, minus pi on A to pi on A, is a reciprocal lattice vector, okay? Everything is a little bit confusing here, but if you keep your eye on this original curve, the dispersion curve, the energy versus K curve, you know, energy is h bar squared k squared on 2m in this case, it looks like this. And here at this other lattice point, G vector, there'll be another curve. Or you can think of what you do is you're coming up here, your curve keeps going here, and you've just flipped it back into the first Brillouin zone. Okay? You've got one coming up here, and you flip it back in there, and so on. Alternatively, you can think about it as, I know that at the next reciprocal lattice vector, I also have a similar curve, and now I'm just drawing the extent of this energy curve, only the part of it that enters into the first Brillouin zone. You can kind of think of it two ways. Okay, so when you were folding, it comes up here, you folded it in there. That's called the reduced zone scheme. Okay, and very often we don't draw the band structure like this. We don't draw it with all of these curves here. We only draw the part that's shaded, like here, because we only need to deal with the first Brillouin zone, because everything inside it can be found at any other point in the crystal just by reciprocal lattice vector. It's just repeated. Let me see how we're going. I think I actually kind of wanted to stop here. Let me just have a peek and see what I've got next. Okay, yeah, I want to stop here because I want to start this on Friday, but I'll just give an idea of what we're going to do next. Okay, we've introduced a potential, but we haven't really spoken about how big or what form that potential takes. So there's two approximations that we need to know about. One is called the nearly free electron approximation, where we introduce a very weak potential and we use perturbation theory to solve things. The other approach is a tight binding method, which assumes the opposite end, that the orbitals are are like very strongly bound orbitals, like you might have s, p, and d orbitals. So they represent two extremes of what an actual crystal might be like. So we'll start with the nearly free electron model, go through that. Then we'll do the tight binding model, go through that. And we will know that in reality, the true answer is, of course, much more complicated to solve accurately. And we do that with supercomputers nowadays. But the answers generally lie between these two extremes. These are very simple models. So I think we'll just leave it here. I just want to say, I think you got an email saying that I put up the formula sheet for the exam. I don't want you to freak out thinking that, last time, years ago, you didn't have a formula sheet, therefore the exam's going to be very different. The exam's not going to be that much different. I just put the formula sheet there because there might be one or two problems that you need to solve quantitatively, and you need to have the formula there for you. And so it might be helpful. Okay? When's it due?